So yesterday we have seen everything about the supervised learning. Today we will see everything about unsupervised learning. So the first speaker of today's lectures will be Ylenia Maruccia from the Observatory of Capodimonte, so from here. Of course, a friend of mine. And let's start this session, okay? So welcome back, everyone.
Thank you, Giuseppe, and welcome to everybody to this session of this morning. I know that you are too tired from pizza and beer yesterday evening, but we have to start. So today, as Giuseppe was saying, we will start the unsupervised learning part. And in particular, this is the outline of today. We will see I will do a first introduction on unsupervised learning, on the main concepts, and in particular on the metrics that we will use to measure the goodness of our results with unsupervised learning. And then we go into the clustering parts. We will see some algorithms, in particular the key means this morning, and after me there is another session with Francesco Schiliro, who will show you the self-organizing maps. And in the afternoon, we will see other clustering algorithms, in particular the DB-scan, HDB-scan, and so on. So I want to start from here and take a broad approach, because in these days we have seen that we are living in a digital transformation era, and what it means. So it means that we have a data deluge, a huge amount of data are generated every day, and in particular, we have to not think for a few seconds to astrophysics, but to the data that we generated ourselves every day with our smartphone, with tablet, with our dispositives. Think about the messages you send, the photo, the pictures that we take outside, or at the coffee break, with all the good things that we are tasting these days, to the, I don't know, to the mail that we send every day. So these are also all the data that we are generating in a very quick manner. So as Farida said last days, there is a huge amount of data, and there is also the velocity in which these data are generated, and the velocity that we need in order to elaborate them, and not only in the generation, but also into the elaboration. And in astrophysics, it is the same, because the data are generated in a very quickly way by all the telescopes and the sky surveys, no? But yesterday we have seen that many of these data, some data of them, needs the labels in order to be analyzed. We need labels, but the world is not so wonderful, and we don't have always labels for our dataset. I was thinking to all the flash talks that you had in these days, and in which you had to go to see and if an object is a star or is a galaxy, for example. Okay, so we don't have them. We are not so lucky to have labels, but at the same time, the missing labels enable us to discover new things. So the paradigm of the unsupervised learning is connected to the discovery, and it is very important. So let's start from this example. We have an artificial intelligence expert, a robot in this case, that finds himself in a chaotic and disorderly library, and he had to order all these books, okay? So yesterday we have seen the supervised learning. We know that there are labels. this expert is enabled from a high quality label data. So each observation has a predefined ground truth. And so we can classify this data or make a regression, okay? For example, we have to answer to a question like, what is this book? It is a book related to classic or science, or when we go into a library. And then the prediction, we have to do prediction and to map these books. Or, for example, we can also use the regression if we want to understand if the books have to be classified by their price, okay? How much does this book cost? So this is the supervised learning, where the learning is guided by a known target, that is the label. And what it happens when we don't have labels? Well, the expert should understand itself the data set, okay? We don't have labels, we can't use a ground truth, so we have to learn from our data. And here it is the difficult part of our job, because we have to understand what kind of data we have. And here there is also the role of the data scientist and the researcher, in which we have to understand our data, we have to understand the model we are going to use, and the results that the model will give us. So it is very important, it is always important to don't lose the focus of our research and of our works, okay? So we need to understand the data and the results. And in here, we have the unlabeled data sets. So we have observation that haven't the predefined ground truth or the target variable. And so we move from the prediction to the representation. So we need to understand the input itself. And the unsupervised learning don't replicate a known answer, but have to reveal the data structures. So we have to reveal the latent structures within the data, the possible recurrent relationships within the data, and to natural groups this data in some way. So on the left, we have the label training, the supervised learning, in which the expert is using these labels and understand if a book goes into fiction, economics, classics, science, biography, and so on. And on the right, we have the expert that order and discover. So he has the possibility to classify these books because he understands the features within the data. Okay, so uncovers hidden structures and patterns within the data, and the role is shifted from instructors to explorer. So the algorithm in the supervised uncover operate exclusively on the feature space, okay? And try to model the underlying probability distribution or to identify the topological properties of the data itself. And also, as I was saying before, it enables us to uncover patterns that would be impracticable to detect manually at scale. And so it allows also to make a decision. Okay, it is very important because it allows us to make decision on what we already know, but on what the data reveals when they are freed from predefined labels. Okay, so it is very important, this step. Here comes the importance also of the validation of results, because we need a lot of experience for the data scientist and the researcher, because, as I was saying, it is important to understand the data, because we have not to stop near our results, but we need to understand if these results are how to say, if these results are good but in a scientific way. So we have to validate their veridicity, the veridicity of our results. And it is, and these steps of the validation is perhaps one of the most challenging aspect of the unsupervised learning, because we don't have labels, and so how to measure the goodness of our results? This is very important. We couldn't use we cannot use the accuracy on the, or the recall, as yesterday we were doing, but we have to measure a set of criteria that combine the internal indicators, for example, how the clusters are compact and well separated from one to another one, the stability with the parameter variations, and also consistency. We need to measure also the consistency with the domain knowledge. So this is how the unsupervised learning in the supervised learning, we try to validate our results. All these things will be much clearer when we will see some example. Okay, I will show you, but also with the tutorial part, we will see some example, and so all these things will be clearer. So the paradigm of the unsupervised learning is this one. We have the unsupervised learning that the aim is to identify structures, and so we have the clustering part that we will see today, that aim to partition the data set into subsets, the clusters, in a way in which we need to have the maximization of the similarity between the elements that belong to the same clusters, and at the same time, the similarity between elements of different clusters must be minimized. So this is the aim of the clustering. Another another paradigm of the unsupervised learning is the dimensionality reduction, and Simone show you something about in the first day with the PCA, the TSP. All these methods help us to reduce the number of input variables. So all these parts are related to the dimensionality reduction, and these simplify models and reduce noise, or improve also the computational efficiency, because we have less features within the input data space. So it is very important also for this. And then the association rules that involve discovering probabilistic relationships and the occurrences between the variables in transactional datasets or relational database. So all these paradigms have some algorithm. The most used algorithm or diffuse algorithm are those ones. K-means, dbScan, HDBScan for the clustering. The latent Dirichlet allocation is a method that we won't see, because it is related to the analysis of textual data, and allows to extract the topic from the data before the generative artificial intelligence to take place. These methods were very diffused, because they allow us to analyze a lot of material from social network, or for the industries use them to extract the topic of, for example, for tourism, to understand what kind of comments the people do when go to visit something, for example, or the hotels and so on. So the latent rich layer location allows to groups terms and to so this is a cluster method, and to understand also with the sentiment analysis if the sentiment is positive or negative. Okay, so we this is not an algorithm that we will see in these days. And so there are also the other algorithm for the dimensionality reduction, the PCA-TSNE, and self-organizing maps. I insert the self-organizing map there in the dimensionality reduction. Today we will see with me this algorithm, and with Francesco the self-organizing maps that I don't know if to be considered a clustering algorithm or dimensionality reduction, but Francesco can explain you why there is this double interpretation of the self-organizing maps. So let's start from here, from the clustering. Are some questions before to go inside the clustering, or I can go? No, okay. Okay, okay. So clustering, let's start from here. So the preliminary concepts. Clustering is the most straightforward and delicate practice because we have two groups, similar observation. And we need an external criteria, some external criteria that can tell us if the partition is correct or not. So operationally, we have, as you can see in this figure, the fluids. We have different fluids here, and we have to understand, we need an algorithm that can tell us if there are orange or apple, I don't know what are there, what are they? Or we have to distinguish between the different kind of fluids, okay? So how to operate, how to understand if each element belongs to the same group or to another one. And mathematically, we have a data set, X, that consists of different objects. And the objective is to assign each point to a finite system of K clusters, okay? Maximizing the internal similarity within groups and minimizing the similarity between the different groups. So this is the mathematical part that we need to explore with for understanding the clustering. And so what do we need to do? Well, we have to collect our data, and we have a lot of available data. So there is no difficulty to find a data set without labels, especially in astrophysics. Then we have to choose the clustering method, but when we choose the clustering method, we have to remember that together with the clustering method, we are also choosing a similarity matrix. And this is very important because when we choose the similarity matrix, that is a distance-based usually matrix, I will show you what are the matrix. We are treating in different ways the parameter space in which we are working, okay? So if we measure the similarity with the Euclidean distance is different if we use the cosine similarity and so on, okay? So this is very important. We need to remember this part. Then we have to train the model, but how we train the model? We will train the model on all the data set because we don't have to distinguish between the training data and the test data because we don't have labels. So all our data set is used to train our model, our machine learning model. And then we need to evaluate the model. And so, as I was saying before, we need some metrics in order that are necessary in order to evaluate, to measure the goodness of our results. And finally, we have to interpret the results, to use the clusters and to understand if these clusters correspond to something in reality, or if the method is not well working. There are different typology of clustering methods, this is the reason why there are typology of clustering methods is because each family belongs to a different perspective on what it means for data points to stay together, to belong together to the same cluster, okay? The similarity and the use of the similarity that we adopt to structure our parameter space. And so this choice is very important because we have to interpret because it has important implications in the performance of our clustering of our algorithm, and also on the interpretation of the results. And these typologies are different because, as we will see, there are different ways to cluster the data. For example, there is the centroid-based clustering, such as the k-means, that cluster points based on the proximity to centroid. So the algorithm finds the centroids of the cluster, and then all the points that are nearby this centroid, we will see how these centroids are searched for and then are used to how to measure the distances of all the points from the centroids. And so k-means is one of the algorithms that work in this way, but there are some problems that I will explain you what kind of problems, for example, the k-means have. And so there are other, basing also on our data set and on what we should do, there are other algorithms that use, for example, the connectivity based or the density based. So the connectivity based, it is the hierarchical clustering, and this is something that we will see in the afternoon, or density based, when we use the density and not, we don't search for the centroids and how nearby are the points to the centroid, but how dense is the clusters, how how distance is the point from the density part of our data set, of our group. And there are also the graph-based methods, for example, the affinity propagation spectral clustering, that cluster points based on the graph distance. So we need to build a graph, the distribution based, in which, for example, the Gaussian mixture models that cluster the points based on the likelihood of belonging to the same distribution. So we need to understand what is the distribution of our data, and the compression based that transform the data to a lower dimensional space and then perform the clustering. Okay, so there are different kind of typology of clusters, of clustering methods. So we have to understand also what kind of models, what kind of model is better for our data set. And these are the similarity or distance dissimilarity metrics. As I was saying, the similarity needs to quantify how alike or different two data points are in a feature space. And so this is important because we have to understand if a data belong to a cluster or not. There are different kind of similarity metrics. The Euclidean distance is the most used, and perhaps is the distance that by default is adopted by many clustering algorithms, and everybody knows how the Euclidean distance is calculated. Then we have the Manhattan distance that is named after the shortest distance a taxi can have traveling across most of Manhattan. So unlike the Euclidean distance, in this case, we have to go around buildings rather than to go straight forward to a line to the short. We don't have to consider the shorter distance, but to go around the buildings in order to arrive to our destination. And the cosine similarity also is very known because it measures the cosine of the angle between the two vectors in the multidimensional space. So it is usually used for high dimensional or text-based data. And the Malanobis, I have problem to pronounce this name, distance that measure the distance between a point and a distribution. So it is very used for the last typology of data, or for data that is not non-spherical and has correlated dimensions. So these are the different metrics that we can use in the algorithm. And the choice, you will understand that if we choose a wrong similarity metric within our algorithm, we are changing the way in which we are trying to cluster the data. So the results could be very, very different. So pay attention to the choice of these metrics. And then the evaluation metrics, the famous evaluation metrics that I'm speaking about from the beginning of this talk, because we have to understand how to measure the goodness of our results. So we have two kinds of measures: the intrinsic measures, in which we have no labels required, because if we have, it is clear that all the unsupervised learning methods could be applied to a dataset in which we have labels, but forgetting that we have labels. So we don't have to train a model with the labels column. It is too simple. We have to treat the dataset as if we don't have labels, and so we train a model in an unsupervised manner, and finally we can measure the goodness of our results, going to see if the clusters, for example, that we obtain are similar, correspond to the labels that we have, the ground truth that we have, okay? And so in this, there are some extrinsic clustering metrics that are used when the ground truth labels are available. But we will see the intrinsic clustering metrics. And they are based on two definitions: the compactness of the cluster, so how close the points in the same group are, and on the separation, so how far apart the groups are from each other, okay? And if we understand this, it's very simple to understand also this first metric, that is the silhouette score. The silhouette score is one of the most adopted metrics to measure the balance, to measure the similarity, the goodness of the clustering results, because we have to define it, this measure, this matrix, we have to introduce the two different definitions. The cohesion, that is the average distance of a Q point in the first figure from all the points in its own cluster. So it is the measure of the cohesion. and the separation, that is the minimum average distance from the same point Q with all the points that belongs to the nearest cluster, but that is different from the cluster in which the Q point is. And this is the measure of the separation between a cluster from the nearest one. If we understand these two definitions, then we can understand also how the silhouette score works, because the silhouette score is the ratio between the difference between the separation of the cluster and for each cluster and the cohesion to the maximum between the separation and the cohesion. So how what kind of values should we obtain to have a good clustering? Well, we need to have a silhouette score near to 1, because it means that the point is well inserted in the cluster and also well separated from the others, because the cohesion each is much less, is less than the separation. But if the points is close, if the silhouette score is around 0, it means that the point is very close to a boundary. So we have that the clusters is good, but there is not a good separation also, and the point is very close to a boundary. So if we change some metrics between the cluster method, the algorithm, that point is not so possible that belong to the same cluster, but it's possible to change the clusters or to be an outlier, okay, a noise point. And if the silhouette score is minor than 0, then is less than 0, the point is on average closer to another clusters than to its own, and so this assignment could be very inconsistent, okay? So the silhouette score works it is very understandable and very easy to be used. Then we have the Davis-Baldwin index that measures the ratio between the intra-cluster scatter and the inter-cluster separation. So what we need to do, we have to measure the intra-cluster distance in this way. There is the first formula of the slide. We have to measure the distance between of each point to another one within the clusters. Then we have to measure the intercluster distances and between all the clusters. And then we define the similarity between two different clusters using the formula that is shown on the third line. No, don't worry. Non l'ho toccato. Okay. And finally, for each cluster, we have to take the maximum similarity value within all the clusters. So the Davis-Baldwin index is the average of each similarity measure, the maximum similarity measure that we have with K, a cluster K to all the other clusters L. So the lower is the Davis-Baldwin index, the better is the clustering. We need to remember this part, and I have prepared a notebook in which we will use this both the silhouette score and the Davis-Baldwin index. Okay, so the lower is the Davis-Baldwin index, and the better is the clustering, because a value approaching to 0 represent a nearly perfect partition. And so the clusters are well separated, and each point belongs to this index explain how much are distant a cluster from another. Okay, so the silhouette score and the Davis-Baldwin are two index that or two metrics that are used together in order to measure in different way how the cluster is good. And often is well to use different metrics in order to measure the goodness of the clustering and not to use only one of these metrics. Then we have also another metric that is the Dan index that evaluates the ratio of the minimum intercluster distance to the maximum intracluster distance. So a high index indicates that the clusters are well separated and compact. It has some advantages. For example, it is very useful for identifying compact and well-separated clusters, but it is very sensitive to noise and outliers. So, and it is also computationally expensive when we have large data sets. So these are some disadvantages. And finally, we have this method that is the within cluster sum of squares, the WCSS, or inertia, and it is very used, and the K-means is based on this criteria because it measures the compactness of the clusters, and this index is calculated in this way. We have to take the sum of the square distances between each data point and the centroid of the clusters, and then we have to aggregate all these values over all the K clusters. And this method is very useful in order to understand, for example, in the K-means, how many clusters do we expect on our data set? Because some clusters needs this input at the beginning. And the inertia, or the WCSS, is very useful for understanding how many clusters do we need. There is the elbow method that I will explain in a few slides this morning that help us to find this the optimal number of clusters to be considered for our algorithm. So I will start from the K-means, and okay, so let's understand how it works. It is very simple. The K-means is a centroid-based algorithm. If you remember the slide with the different typology of clustering, and in which each observation is assigned to the clusters whose centroid is the closest to it. Okay, so we need to measure the distance between each point from another one, from the centroid that the methods is choosing. And at the beginning, the clustering, the K-means finds the centroid in choose some points as centroids, and then it has to understand if these centroids are good or not. So these are the steps. We have to, there is the initialization of the centroids. So the algorithm begins by selecting K initial centroids, and then chosen at random. And then we have to assign each data point, the step 2. The step 2 is showing you in the figure the initialization of the centroid. Okay, so the stars, green and blue, are telling you that the K-means has choose these two centroids. Then we need to understand all the points that are nearest to one centroid or to another one. And so how to do it using a distance matrix. In this case, the Euclidean distance is the default matrix. And in the step 3, we can see that all the points in blue are the nearest to the centroid, to the blue star centroid, and the green ones are the nearest to the centroid in green. But if we see this figure, we know that these points are not the real centroids of the cluster, because the clusters are not well represented. But this is also the first iteration of our method. So we have to, there is another step in which the centroid is updated, and based on the distance of the all the points, and then we have new centroids assigned, and the k-means will calculate another again the distance between the new centroids and all the points, and understand if the point is nearest to one on the other one, to the first centroid or the second one. And then all these steps are repeated again and again and again. Why, when the algorithm will stop? Well, if we have given a maximum number of iterations, so there is by default, I don't remember, I think that by default is 100 iterations in the k-means, but if we these centroids change the position, then the k-means will stop at the maximum number of iterations reached, or when the cluster's assignment no longer changes, so the points are of each cluster are the same, or if the centroids finally stabilized their position. Okay, so and all this is done by using the minimization of the inertia of the within cluster square sum of square. Okay. What are the advantages of the k-means? Well, it is very efficient in a computational way. It is very fast, and usually it is the first algorithm that we use when we have to explore our dataset, and we have to make a clustering on our dataset. There is also it is also scalable. We need it is able to handle millions of records efficiently. It is also very easy to interpret the results that we have, and also the parameter space is not changed, and so we have the control on our parameter space, and we understand what has been done by the algorithm, and also it guarantees the convergence to a results. Okay. These disadvantages. Well, the first one is the initialization of the centroids, because we understand that we have two kinds of configuration, the good start and the bad start. The good starting when the centroids are very near to the real groups that we expect from our dataset. But remember that we are not, so I'm showing you all the plot, but in which we have two features, and it is very easy to interpret the results. But in reality, we know that we have a lot of features at the beginning, and how to understand which one could be the best to represent our dataset. And so there is the dimensionality reduction, the PCA, the two component, and so on. But okay, let's think to a very simple example in which we have these clusters represented in this way, and we we can see that the good start is on the left side of the plot and the bad start is on the right. So also in this case is very simple the way in which the centroids are updated. In the first case, in the good start, there is we will need also only a first iteration, only one iteration in order to move the centroid. The K-means is very fast to understand that the real centroids are those ones represented in the second plot, in the plot on the right. But when we have a bad start like this, we have the centroids in the first step that are moving towards the real cluster of the data. And at the step 2, we have an inertia that is very low, 0.35, and the accuracy is 100%. But I want to say again that is a very simple example, and when we have a lot of data and a parameter space that is very that has a number very high of features is not so easy, and we need a lot of iteration in order to understand if the centroids to understand the real centroids and so on. Then, for example, this is another example in which the centroids, we need different iteration in order that the centroids comes to the real position and identify the real cluster. But I want to go on in order to have time for the tutorial. So a way in order to go beyond this problem, there is the K-mean plus that instead of placing the centroids completely at random, it spread them out to avoid the poor initialization that we have. So this could be a solution to this problem. Then the main disadvantages, I think, that is the fact that we have to indicate the number K of clusters that we expect from our data set. And how to do this? Because we have to because we have to understand also that, for example, in this figure, we expect at the first sight, we expect 2 clusters, but if we see in a different way the figure, how much cluster here do we need, 2 or 3? And so we use the elbow method using the inertia that we defined before. And how to use this? Well, we have to plot, we have to searching for the best K, the best number of clusters. So we use the K-means. We iterate for a number of K clusters that we, I don't know, that we want to understand how many clusters. And then we measure the inertia, the within cluster sum of squares. And we plot, we plot on the x-axis the number of clusters and on the y-axis the inertia. And then we see when the slopeness is changing. This is the elbow. We have to identify the elbow, and usually this is the good point, the good number of clusters that we could give to our K-means in order to cluster our data. Okay, I think that I can go on from this slide. Another way to measure to try to understand the number of clusters that we can give to the K-means is to evaluate the index, the Davis-Baldwin, the other metrics, the Davis-Baldwin index and the C2H score, because If we see the Davis-Baldwin, how in varying the number of clusters, how the index goes, we said that a lower Davis-Baldwin index mean a good clusters compactness of the clusters, and so we need to search for the minimum of the Davis-Baldwin index. In the silhouette score, we need to see how nearest is to 1 the value, but usually we have a maximum. And so from this plot on the right, you can understand that, for example, here we have that the 3 is the best number of clusters that we expect from our dataset. But there is also the silhouette plot that we can build and on our dataset. And there is a simple model a simple plot in order to see the distribution of the silhouette score values within the clusters. So these are all the points within the clusters, the silhouette plot for the various clusters. And this is done, for example, on the IRIS dataset. And the dashed line represents the global average score. So if the average is low, it implies that the populations, the clusters are not well separated, but if the mean goes towards a high score, it is well separated. And sometimes we could have some negative values to the silhouette score values, and this corresponds to misclassified object. Okay, so when you see these negative values, it means that it is not wrong. It is wrong. Sometimes it is wrong the results of the cluster, but it is not wrong to have silhouette values less than 0. Then another very important disadvantage of the k-means is the fact that it is based on a spherical cluster. It searches for spherical clusters. And so, for example, if we have the clusters as in the bottom left part of the slide, you can see that the ideal clustering is this one and not the clusters that the k-means performs. And it is a very important disadvantage, because the k-means in this way will include all the points within the clusters. All the points will belong to a cluster. And so if we have noise, we don't have the labels that say us it is an outlier because it is it not belongs to a cluster. Okay, so all the points are allocated to clusters. And so this is the k-means, but what if we have the data structures that, for example, have irregular shapes, as these ones, for example? So what happens if we have irregular shapes, a variable density, or we have some observation that don't belong to any group? Well, we will see this in the afternoon, and now it's the time for tutorial, because then we have also the coffee break at 11. So we will start the tutorial now, okay? I think that I have shared you the tutorial on the Indico page, and so you can download it, or if you, I'm using the collab, so if you want to open it within Google Drive with the collab, it is very fast, and you don't need to install anything. So I have you the tutorial in order to follow me within the code, and if we have problem to understand how it works. I am starting. So I don't know if you are on the collab, you don't need to install nothing, but anyway, you have to install only this library, because all the other one I are already installed within the usually the Jupyter notebook, but I think that Giuseppe gave also the IP widget, no, in the, okay, so nothing. So sì.
Sorry, I didn't understand. It's the same libraries of Giuseppe, right? Basically.
Sì.
Okay.
Okay. Okay, so the first part is only to load all the packages that we need. As you can see, we need very simple packages, because I'm using the NumPy, the matplotlib to visualize the plot, the seaborn, in order also to set some settings for the plots, in order to have a font scale that is readable for all of us. And then we need some packages in order to, I'm using the make blobs and the make moons in order to build different kind of data sets, to generate different kind of data sets, in order to show you how each method works on this data set, okay? And but we will see all this part while I'm doing the thing. So the first thing I'm doing here, in the afternoon we have to I have I gave you a notebook in which there are 3 or 4, I don't remember, exercise. I generated 3 or 4 different data sets with different shapes and density, and so you have also the possibility to understand which kind of algorithm we can use on these different shapes that we visualized. So the way I'm generating this data is the same. I'm using these make blobs of the scikit-learn packages, and I'm telling the Python library, to the Python, how many samples, so how many points we want, how many features, only 2, many centers do we want to build our data set. Okay, so if I execute this, I have the 300 points and only 2 features, and the Y is telling us the clusters to which belong, because the centroid to which they belong, okay? So we have the label, but we don't use the label to clusters the data. And here there is the representation of our generated data set. I don't know if there is another way to visualize perché così forse. Devo diminuire un po'. So this is the distribution of the data that we have generated. Okay, so we have 4 different clusters, as I was saying, as I told to Python, and then we need to pre-process the data. We are using the clustering, and we are using the k-means. This is a centroid-based algorithm. We need to scale the data because it is using the distance matrix. So it is very useful to scale the data in order to don't have problems with the similarity measures. And so I'm using the standard scaler in order to scale my data sets, and as you can see, the shape of the data are the same, but we have different values because they are scaled, and in fact they are also with the standard scaler we have the mean around 0. Okay, so this is the how the data has been converted into the scaled space parameter. Then we have to use the Elbow method because we need to understand how many clusters can we have in our within our dataset. This is the code. So I have to if I think that you are good in Python because you are using it in these days. So we need to add the inertia values that we are calculating in our iteration of the k-means model. So this is the loop cycle to understand, to calculate the inertia varying the k in the range between 1 and 11, as it is shown there. And then, so we evaluate the k-means. This is how we perform the k-means. So we have to indicate the number of cluster k. The initialization of the centroids, that is automatic, so I'm not doing nothing here. And then a random state that enable us to repeat the experiment and to have to obtain also always the same results, because if the random state is not set, then we can obtain different things. But it is only to make repeatable an experiment. Then we have to fit the model on our data, the X-scaled, and then to append to our results of the inertia we obtain. Okay, so the inertia is an output that we have from the k-means model. And so at the end, when we have when this loop cycle is done, we can visualize our data, our inertial values within this plot figure. I don't want to go because there is already the results. And here you can see how the inertia is going at the number of clusters, as the number of cluster varies. And as you can see, the elbow could be, but then we have a minimum at 4. So we expect 4 clusters, and we know that I gave to the Python the code in order to build 4 clusters. Okay, so the inertia is telling me how many clusters is better to give to the k-means. There is some explanation here, but then we could also evaluate this the silhouette score, and here is the way in which we can calculate the score. Always we have to have here. Sorry, it is the way in which we evaluate the score. So we have to do a cycle for varying the k values, and then the k-means, we have to set the model of the k-means, indicating the cluster, the initialization, the random state. There are also other parameters, but they are the base parameters. And then we have to fit on the scale, and then we evaluate the silhouette score from the scikit-learn packages. I have imported this one at the beginning, and the silhouette score is calculated passing the scaled, so the values, the feature that we are using for training our model, and the cluster labels that are obtained by the models, the K-mean models. And finally, we can visualize the results in the plot. This is how to build the plot, okay? And this other code is only because I built this annotation of the plot. So also in this case, you can see that 4 is the best silhouette score. At 4 clusters corresponds to the best silhouette score, that is the higher values that we have. And so also the silhouette score is agree on the fact that the K equal to 4 is the magic number to adopt in our clustering. I have also inserted this code that allows you to see, but I need to show all the plot. This is in this code that you can see the interactive plot, and so how the silhouette plot is changing at the variation of varying the number K of clusters. And so you can see, for example, that here there are some negative values, as I told you before, that it is possible to have this, but you can see also how this plot is changing at the variation of the number of clusters that we can give to the K-means. And as you can see, the K equal to 4 is very good. The results is very good because we have an equal distribution of the number of points within the clusters. The average is not near to 0, and so on. But if we, for example, choose another 5 clusters or 6 clusters, then you can see that the points are become to be distributed in a different way within the clusters, okay? So this helps us to see that K equal to 4 is also a good value. And also in this case, you can see the centroids, how the K-means have choose the centroids, because we can have this information with this line. We can understand what are the centers of our clusters with the K-means, and you can see also how these centroids are where the centroids fall into this parameter space when we choose different number of clusters, okay? So you can see, for example, that with K equal to 5, the last clusters is separated into clusters, but it is not so good. Okay, so this is how the data are separated when we consider different many clusters than 4. So K is the best number of clusters, and so we have to train our model and to predict the clusters. And here is the final results that we have. I also prepared this code in order to see how the centroids move, and the inertia also move when you pass from when you pass from an iteration to another one, okay? So at the beginning, iteration 0, these were the random points that the k-means select. And so the inertia is this one indicated here. At the iteration 1, the centroid is moving from the previous in blue to the newest point. So the calculation has been done, and so we have different points that belong to the clusters, and so this is how the clustering is working. In order, if you can see, the inertia is diminishing in the S values, and here you have the last movement, because if you can see here, the separation between the previous and the current centroid is very, they are very near. And in fact, at the end, you have the inertia that is not changing, and also the position of centroids that remain the same. And so this is how the k-means is working, okay? And finally, what it happens when we have irregular data, such these ones. Well, the k-means, the data scaling, okay, we visualize the data scaled, okay, but when we apply the k-means, this is how the k-means is clustering these irregular shape data. And so this is a problem, because points don't belong to the right clusters, okay? Because we expect in the data generation, I set 3 groups of data. That is the first moon shape, the second one, and the final clusters that is denser there. And so we expect 3 clusters, but the k-means is not understanding the real where the points belongs to the what kind of how the points are belonging to the clusters, okay? And so in the afternoon we will see how to solve this problem. Here also there is the interactive version of the data, the elbow on the k-means, but I will explain you that the elbow with irregular shape in the dbScan, when using dbScan and so on, is not good to use. In fact, as you can see here in this data set, in which we have irregular shape and irregular density, the elbow, okay, is good, but it is not so good and not so efficient as in the data set I generated for the k-means, okay? So these are the problems that we will see in the afternoon and how to solve them. So if you have questions on this data set, on this first part, you can do it. We can discuss later at the coffee break, or in the afternoon. I am here, and we have also the hands-on part in which you have to write the code. So as you want. Thank you for your attention, and have a nice coffee break.
So, are there any questions? There is a little bit of time before the coffee break, so.
Thank you for the presentation. Very, very thoughtful and useful. My question is I have a clustering method that's called Gmode. It's very planetary science, and the problem is a bit. You for example, if you identify like 3 clusters, 4 clusters, but sometimes because there are some let's say random operations, the same 4 clusters that I identify is not the same can be not the same every iteration, every time you run the code. So what is the best approach in this case? Is to like, I will have several silhouette scores for the 3 clusters, for several. I mean, how I would approach to decide what's best in this case.
So you have
yes, like I run Like,
Okay.
let's say, decide that that's 4 clusters, but for 4 clusters, sometimes can have slightly variations
Okay.
in the final product. So how I would decide what's best in this case?
Yeah, it's a very good question, because as we can see also in the afternoon, I have generated this data set that I'm showing you, but at the final, at the end, we don't have the way to decide well the number of clusters that we have at the end, because it is very difficult also in real data set in which we don't have labels and so on. So I think that at the end you can also see how good are the results, also based on some features that you have. For example, inspecting also the parameter space, visualizing, adopting other kind of clustering, other algorithm, the PCA and so on, in order to understand if you are for example, the features that I don't know, the features that you use, if there are some features that can help you to understand well if the clusters is how many clusters are good and so on. I think that you have to interpret all the final results using all the things available that you have at the end, because or trying to measure other metrics in order to see how the variation of this metric also is. I think that it is a good approach, not only using a parameter, but trying to understand all the things that are available.
Okay, thank you.
Are you agree?
Okay, we have another question there.
See.
Thank you, Ylenia, for your clear and detailed explanation. And I don't know if it's probably the same question before. Probably it's a trick argument, but I suppose that for evaluating the number of clusters that you want to figure it out, you use all the silhouette score, we say, and also the elbow method. To be sure, I think, I suppose that to use both, no? But if it could be the cases where both method suggest you different number of cluster. Okay, in this, from the question before, I understood that it belongs to us to decide.
Yeah, because we have to understand also, the data, and we have to understand, the results, and to see how many information we can extract from our data set and from the results, in order to understand what is the good choice we have to make, because it is not so simple.
Okay. Thank you. So at last we made 2 different model with 2 different use case of clusters.
We can also compare those.
The final result
to compare
evaluate
the results at the end, because there is not an optimal choice
Okay.
at the end of these methods.
Thank you.
At the end of the machine learning, we have never the optimal choice.
Thank you.